All right, today we're going to dive into a technique that is, it's one of the absolute classics in the hacker's playbook, the Stack Overflow. We're going to see how just a tiny, simple programming mistake can be weaponized, turned into a master key that lets an attacker totally corrupt and take control of a program's flow.
So let me just start with this question. What if you could literally grab the steering wheel of a running program? Instead of it doing what it's supposed to do, following its own code, you could force it to go wherever you tell it to go. That's exactly what we're talking about today.
You see, normally, a program's execution is like a car with a super strict GPS. It goes from point A to point B, then to C, precisely as it was designed. There are no detours, no unexpected turns. It just follows the map.
Now, things get really interesting when a program takes a little side trip, what we call a function. Before it goes, it has to leave itself a note. It has to write down, hey, when I'm done with this task, this is where I need to come back to. That little note is the return address. It's basically its ticket home, and it's absolutely crucial for keeping everything running smoothly.
So where does the program keep this super important ticket home? Well, it stores it in a special place called the call stack. And this place, this stack, turns out it's the program's Achilles heel.
The call stack is just a temporary workspace in the computer's memory. The easiest way to think about it is like a stack of plates. Every time a new function gets called, the program puts a new plate on top. And on that plate is all the info for that function, its variables, and, you guessed it, buried in there is that all-important return address.
So here's the normal, happy path. The first function puts the return address on the stack. The program then jumps over to the new function and does its thing. Once it's all done, it just looks at that address on the stack and jumps right back where it came from. It's perfect, it's orderly, it's secure. Or is it?
And this is where it gets fun. What if we could send so much data to a function that it doesn't just fill up its own little workspace? What if it starts to spill over, kind of like an overflowing cup of coffee, and that spill goes right on top of our precious return address?
So, take a look. On a healthy stack, everything is neat and tidy. You've got your buffer, that's a space for data, maybe a password you type in. And sitting right next to it, safe and sound, is the return address. Everything's in its place.
But now, look at this. It's chaos. We've just shoved way too much data in there, a whole bunch of A's that the buffer just can't hold. It spills right over and completely smothers the original return address. Our program's ticket home? It's gone, replaced with our junk.
Okay, so this is the fork in the road, right? What happens next is everything. If we just scribble over that address with random garbage, the program tries to jump to, well, nowhere, and it just crashes. Boom, segmentation fault. But, and this is the really cool part, what if we don't write garbage? What if we very carefully write a new legitimate address, an address that we choose? Well, that's not a crash anymore. That, my friends, is a hijack.
Okay, let's pull off our first heist. We're going to look at a super simple program that asks for a password. Now, our goal isn't to guess the password. No. It's to bypass that check completely and just force the program to think we passed.
Every good heist needs a plan, right? Here's ours. Step 1. Find the offset. We need to know the exact distance from our buffer to that return address. Step 2. Find the target. We need the memory address of the function that says authenticated. And finally, step 3. Craft the payload that pulls off the whole thing.
After a little digging around with a debugger, we find it. The magic number is 28. Yep, 28 is the key to the whole thing. It means we need to send exactly 28 bytes of, well, anything, just junk, and the very next thing we send will land perfectly on top of that return address.
So our payload is actually pretty simple. We send 28 junk characters, let's just use 28 A's, and right after that we stick the exact memory address of the valid function, the one we want to run.
And just look at this result. Normally, you type a wrong password, you get invalid. Simple. But when we feed it our special payload, the program goes to check its return address, its ticket home, and it finds the new one we wrote for it. So it obediently jumps right to our valid function, and bam, authenticated. We just totally bent the program's logic to our...
Okay, bypassing a password check is one thing. That's pretty cool. But let's raise the stakes. What if we could do more than just trick the program? What if we could use this vulnerability to get a full command shell, giving us direct control of the system? Now that is the grand prize.
In our next victim program, there's this little function just sitting there called give_shell.
And here's the thing. Under normal circumstances, the program never, ever calls this function. It's like a secret door. But for us, it's a big, glowing target.
So back to the drawing board. We do our recon again, because every program is built a little differently. For this one, the magic number, the offset we need to reach the return address, is 140 bytes.
The plan is exactly the same, just with a bigger number. We build a payload with 140 bytes of junk data, and we tack on the precise memory address of that hidden give-shell function right at the end.
And this is the ultimate takeover. The program is supposed to just print goodbye and then close. But when it gets our payload, it overflows, jumps to the address we gave it, and instead of closing, it hands us a fully interactive command shell. We're in control of the system.
Now, a really quick but important disclaimer. This is a foundational exploit. Modern operating systems have a bunch of defenses against this kind of thing. For example, many of today's shells have protections built in that make them drop their special privileges if they think they're being run in a sneaky way like this. For our demo here to actually work, we had to do a little tinkering with the system's default shell. It's this constant cat and mouse game between attackers and defenders.
So let's wrap this all up. What's the big lesson here? What have we really seen? We've learned how to turn a simple, tiny mistake into a state of, well, controlled chaos. This really gets to the heart of it. A single, seemingly minor bug, like not checking the size of user input, isn't just a bug that might make the program crash. It can literally become a master key, shattering the program's integrity and handing the controls right over to an attacker. And that leaves us with a pretty big question, doesn't it? We've just seen how a few carefully placed bytes can completely subvert a program's logic. So it really makes you think. If one tiny, misplaced byte can hand over the keys to the entire kingdom, just how secure is all the software that we rely on every single day?